Swayam Prabha. Digital India. Educated India.
Already reviewed what we discussed in last class. So in today's class, we are going to discuss indirect recombination. So these gentlemen here, William Shockley, Robert Hall, and there is another guy whose photo is not available here, Reed. So this model is called Shockley-Reed-Hall recombination because these gentlemen, they derived the equation governing the indirect recombination, right? So let us see how they derived. So we have already discussed the trap assisted recombination, right? So there is a trap level here, you can see in the middle. This is a trap level. Now these traps can capture an electron, or they can emit an electron, or they can capture a hole, or they can emit a hole, right? So electron capture is basically electron from the conduction band is captured by the this trap level, or electron emission from the trap level, electron goes to the conduction band. Hole capture, hole goes from the valence band to the trap level. What does it mean? Electron goes from trap level to the valence band, right? So these two processes are basically same. Hole emission, this trap level will give a hole, right? What does it mean? It will take electron from the valence band, right? So this will create a hole there. So that is hole emission. So now we have two processes, right? One governing the electron concentration in the conduction band, and other two processes governing the hole concentration in the valence band. So the first process, we call it A, that is electron capture, and B is electron emission. So dN by dt will be sum of these two processes algebraically, right? So that means minus dN by dt, or recombination, right, will be capture minus emission. Similarly for hole also, capture minus emission, right? Now capture will depend on what parameter? So we have capture coefficient Cn. So Cn is the capture coefficient, right? Multiplied. Now when the trap has to capture the electron, there should be electron in the conduction band, and there should be empty state in the trap, right? Then only electron will be captured. So this capture rate will depend on number of available electron in the conduction band and number of available empty state in the trap level. So it is n times pt. So n is of course electron concentration, p is hole concentration, right? And total number of traps is capital NT. Out of them, small nt are filled and small pt are empty. So that means small nt plus small pt is equal to capital NT. So total number of state is filled state plus empty state. So this electron capture will depend on number of electron multiplied by number of empty state. Similarly, electron emission. For electron emission, this trap level should have electron, right? So it will be simply coefficient times small nt, where En is the electron emission efficiency. Now, of course, emission and capture will be related. You will see next slide. Similarly, for the hole, capture coefficient will depend on number of holes here in the valence band times number of filled traps, right? Because only a filled trap can capture a hole. That means it can give electron to the valence band. Similarly, emission, for emission, this trap level should have hole there, right? So empty state should be there. So then only it can emit a hole to the valence band. So these are two processes, right? Electron capture, emission, and hole capture emission. Is it okay? Now let us see the picture. Let us say total how many states are there? 1, 2, 3, 4, 5. Right? Out of them, this 2 is filled and 3 is filled. Right? So out of 5, 2 are filled. So these 2 become small nt and 3 become small pt, because 3 are empty. They don't have any electron inside. Now let's say one of the electron or hole, they move. Such as this electron is going and it will settle in one of the trap, right? So now what will happen? Now 3 are occupied, right? So now nt become 3 and pt become 2. Now if hole goes, now where the hole will sit? Hole will only sit in the filled one, right? Because that is basically taking the electron out. So this hole capture. The hole capture again, it is reduced to 2 and it has increased to 3. Now empty ones are 3 and occupieds are 2. So is the process clear? Okay. Now how the capture actually takes place? You don't have to remember all this. It is just a derivation and to help you visualize the picture. But the final result will be important for this course. So, but this is just to understand how the what is the mechanism behind this recombination, trap assisted recombination, right? So capture is basically done by the trap states, right? Trap energy levels, right? So let's say the density of trap is capital NT. So density is of course per cubic centimeter, right? Now electron velocity is determined by the temperature. So all of you can recall half mv square is 3 by 2 kt, right? So that gives you velocity is 3 kt by m. So that comes out to around 10⁷ centimeter per second for at 300 Kelvin, or you can also write 10⁵ meter per second, right? So let's say in time, small time t, right, with velocity v thermal, the electron will cover distance v thermal times t. So if the cross section area is a, so the volume enclosed will be a times vt. Now in this volume, how many traps are there? Now there are two types of traps, right? Nt consists of small nt and small pt, right? So which of these state will capture electron? Only the pt will capture an electron, right? So when electron is entering this surface area, means along the surface, the area is a, what will be the cross section of the impurities? Let's say each impurity has cross section sigma. Okay, sigma is a cross section area of each impurity, right? So if electron comes within its range of sigma, it will be captured, right? It will fall down to the impurity level. So if sigma is the capture area and the volume is A times V thermal times T, right? So and Pt is the density of empty traps. So total number of empty traps will become density P times the volume, right? So this Pt times A times V thermal times T, right? This tells you number of traps, or you can say empty traps, right? So these are within area A, right? That electron will encounter in time t. So number of traps per unit area will be, you have to divide this thing by A, right? So that becomes trap density per unit area. This will give you the trap density per unit area. What will be the value? you cross A, right? You get PT times sigma n V thermal times T. So this will be the trap density per unit area. So dN by dt will become trap density per unit area multiplied by the concentration of electrons. Now, if you want to get the rate per unit time, then you have to divide by T also. So this multiplied by N divided by T. What will you get? PT N sigma B, right? PT N sigma B, right? So sigma B is called capture coefficient. So sigma B is defined as capture coefficient. So basically you see here your dN by dt comes out to be, of course it will be negative because this electron are getting captured. So Cn times Pt times N, right? And that's what we saw in previous slide, right? Due to the capture, it is Pt times N. And similar will be the opposite process, the emission, and similar will be the process for capturing the holes, right? The only difference is that capture depends on the carrier, emission depends on just on the number of states that are occupied or empty for electron and hole respectively. Correct? So this is a mechanism. Now let us see. I was talking to you in the discussion in the beginning under equilibrium, right? And now in equilibrium, each process self balances, right? Each process self balance. So that's a electron captured is equal to electron emitted. Hole capture rate is equal to hole emission rate, right? Then electron moving to right, crossing the right interface and coming in from the right interface, or electron moving out of the volume or inside the volume. Holes, number of holes moving outside the volume and inside the volume, right? They basically self balance. So this is basically equilibrium. So in equilibrium, individual rates will be zero, right? The recombination rate for electrons and holes both will be zero. And if you write both of them to be zero, what will you get? You see this expression here. Okay. If this Rn and Pn is zero, what will you get? You can write Cn times Npt is equal to En times Nt. Right? Now NT-PT will be related. So basically you will get relationship between Cn and En, right? So that you can see here. Okay. So En you can write. See, emission is En times Nt is equal to capture times Cn times Npt, right? Now subscript 0 is given just to denote the equilibrium values of these parameters, right? So you can define emission rate in terms of capture. So your En becomes Cn times Pt times N by Nt. Now this term Pt N by Nt, we call it N1. Now Pt by Nt will be how much? Pt by Nt. Now Pt you can write capital Nt minus small nt, right? So this basically boils down to capital Nt by small nt minus 1. Now can you recall what is this? Capital Nt by small nt, or rather small nt by capital Nt. This is the probability of trap state being filled. So this will look similar to the Fermi-Dirac distribution, right? Of course with some degeneracy factor, but this will be same as Fermi-Dirac distribution, right? So it is inverse of this, so it will become 1 plus exponential, where 1 will cancel, so you just have some exponential function there, right? So your En becomes Cn0 times N1, and N1 you can define. Now N1 is basically N naught, where N naught is simple carrier concentration, Ni exponential EF minus EI by KT, and NT by N naught, you can recall this small nt by capital NT is 1 over 1 plus exponential E minus EF by KT, ET minus EF by KT, right? That we have discussed while discussing the doping. And this is basically same expression, because if you substitute here, you will get G here in the factor, right? Because this ET will come here and KT log GT divided by KT, so KT will cancel. Exponential log GT will come as GT here, right? So you can also write this expression as 1 over 1 plus GT exponential ET minus EF over KT, right? So because plus minus means it can be GT or it can be 1 by GT. So it can be 2, 4, 1 by 2, whatever. Right? So this is just to take care of different degeneracy effects there. So when you multiply this, what will you get? Your N1 will be N naught times capital NT by small nt minus 1, right? So you will just have this exponential. So you multiply this exponential term with this EF minus EI, EF will cancel. So you will have ET minus EI by KT. So this is your expression for N1. Now N1 is just a constant, which depends on the trap level and the intrinsic energy level. Similarly, P1 is also a constant, which depends on intrinsic level and the trap level. Now, if you multiply these two, what will you get? ET minus EI and EI minus ET. They will cancel. So you will get very simple relationship. N1 P1 is Ni square. Correct? Now let's assume that the constants En naught, Pn naught that we have calculated under equilibrium, they are not going to change when we move away from the equilibrium. Right? That's the assumption. That these emission and capture coefficients, they remain almost same with their equilibrium value. So we can use this relationship now. So En can be substituted as Cn times N1. So your modified equation will be this En times Nt becomes Cn times N1 times Nt, and capture becomes Cn times N naught times Pt, right? So now Cn is same, so you can take Cn outside. You have N1 Nt minus N naught Pt, right? So when you solve it, so this is the equilibrium, right? From equilibrium we have calculated the coefficient, right? Basically what we have done, we have eliminated this emission coefficient. We have got emission coefficient in terms of capture coefficient only, and capture coefficient is sigma V thermal, right? Okay. So in steady state, they are not individually zero. They are not individually zero. They are equal, so that recombination of electron and hole, they are equal, right? But they are not necessarily individually zero. That is a steady state, right? So if you solve for you can write the equation here. Rn is recombination rate of electron. So capture times Cn times N times Et minus emission. Now emission we got Cn times N1, right? En is Cn times N1, right? So you can write Cn times N1 times Nt. Similarly for hole, Cp times P times Nt minus, again Ep you can write Cp times P1 times Pt. Now you see here, if they are equal, right? So both the equations are equal. Cn Npt minus Cn N1 Nt equal to Cp Pnt minus Cp P1 Pt. So can you eliminate and get the expression for maybe small nt from here? Because Pt you can substitute capital Nt minus small nt, right? So you have equation in terms of Cn Cp and capital Nt, small nt, and N1 P1, right? So from this you can get the expression for small nt, right? In terms of Cn Cp, N1 P1, right? Now when you substitute this expression for nt here, right, you will get the expression for Rn or Rp, right, which we define as recombination rate. That comes out to be Np minus Ni square divided by tau P times N plus N1 plus tau N times P plus P1, right? And tau N is 1 over Cn Nt and tau P is 1 over Cp Nt. So it is basically whole lifetime is inversely proportional to the capture coefficient times the trap density. So that means if you increase the trap density, then the lifetime of the carriage will reduce. Similarly, if the capture coefficient of the traps, right, is increased, then the carrier lifetime will be decreased. Correct? So in this case, now it is possible that electrons and holes, they can have different carrier lifetime. Correct? So electron and holes can have different carrier lifetime. Now you would be of course interested to know what are the typical values of these parameters that we have discussed, right? Now we don't usually intentionally put trap unless there is a requirement, right? Let's say you want to make a material whose carrier lifetime is very less, then of course you will put the traps there, right? You will dope it with impurities which create a energy level in the middle of the band gap. And for fabricating the devices such as BJT or MOSFET, you would like to minimize the trap levels, right? So for that, we have to remove the impurities, right? So that it increases the carrier lifetime, right? So the typical values are listed here. For example, for silicon germanium, right, the trap density is around 10⁻13, right? And the cross section is around 10⁻⁻15 meters square. So very small, it's very small, right? And these S and SP we have not discussed, but these are surface recombination parameters, or it's also called surface recombination velocities, right? And this the energy of the trap level, right? So usually is defined in the middle. So if you take the middle one, so is defined with respect to EI. So if the trap energy is same as EI, it is called efficient trap. These are called efficient traps. If they are away, right, then they will not be efficient, because a trap here will only deal with electrons. A trap here will only deal with holes. It will be difficult for the trap to deal with electrons, right? So if it is the middle of the band gap, then that trap will become efficient. So this energy is actually measured from the middle of the band gap.
Sir, sir, that energy band is of that of dopant or what, sir?
No, can you say again?
How is that trap is created actually?
Oh, trap is basically impurity. like we dope, right? We dope with 357 with boron, or for example silicon we dope with boron or arsenic, right? They create an impurity level, right? But
Yes,
their
sir.
impurity level is close to the band edge, right? So they are
Yes, sir.
called shallow energy levels. They are also like trap only, right? But such as gold and other material, they can create some metals, they can create a energy level in the middle of the band gap, right? So for them, for such materials, we don't call them N or P type dopant. They are called traps basically, because they don't help to create the electron or hole concentration. They act as a trap who increases or decreases the carrier lifetime.
Okay. Sir, here we are considering energy levels of silicon. Let us consider silicon, sir. We have
Okay.
two things, no, sir: valence band and conduction band.
So this is the valence band, and this is the conduction band.
And the energy level we are considering for the dopant, that is for trap, you are saying. What is that, sir? Is it valence band or conduction band?
No, traps are in the middle of the band gap. Traps are in the middle of the band gap.
Yes, sir. That trap, you are saying it as energy level, no?
Yeah, so its energy level is close to EI, the intrinsic energy level, or you could say intrinsic Fermi level.
Okay.
See, its efficiency will decrease if it moves away from the middle of the band gap. If it moves down, it will be difficult for it to deal with electron. If it moves up, it will be difficult for it to deal with holes. So the most efficient will be the one in the middle of the band gap. It can basically trap both electrons and holes. Okay, so next. Now molecule carrier lifetimes, right? So these recombination generation centers are impurities that were unintentionally incorporated, right, into the lattice. Right? So, for example, the gold, which create just in the middle of the band gap, create a trap energy level in the middle of the band gap. So, what is done basically? There are two types of requirement, right? For example, you want a large lifetime, you want a very small lifetime, and some middle lifetime, right? So you can see here, if the T naught is 2 millisecond, is a microsecond, right? Is few hundred nanosecond, right? So if you want to get a small lifetime of few nanohundred, you have to increase the trap. So your capital NT should increase, right? Because your lifetime is proportional to 1 over capital NT, right? You want to have some medium range of lifetime for your PN junction devices, then you should not have a large concentration of traps. It should decrease, right? It should be manageable basically, right? Or you can decrease it, right? Now in some cases you need a long lifetime, right? So then this NT should be actually lowered, right? Especially lowered, right? So this you can achieve by a clean process where you reduce this uh, gold particles or metal particles. But even after that clean process, some gold particle or metal particle remain there, right? So what is done there to increase the lifetime? These gold particles are removed. So how they are removed? They are made to react with some other material. So for example, if you diffuse the phosphorus from the back side of silicon, right? So this phosphorus will basically, it is basically a trap for the impurities, right? It will trap the impurities, and this process is called gathering. This process is called gathering. So by that basically you can control the concentration of impurities and therefore the lifetime, the carrier lifetime. Now again we will discuss low level injection. You can also consider a situation of high level injection also. Yeah, please.
So what is meant by the trapping of impurities?
No, gathering is basically you are removing the impurities. Now impurities you cannot pull them one by one using some mechanical device. So it has to be done through chemical route. So chemical route is basically you inject phosphorus there, and they will interact with the impurities and they will attract the impurities to themselves. So that because we are injecting phosphorus from the diffusing phosphorus from the bottom, so these impurities will be attracted to that particular site. So that upper layer of your semiconductor will be free of the impurities.
Okay, sir.
Sir, do they trap only impurity ions or some else?
Okay, it depends on individual kinetics, but it is found that these phosphorus atoms tend to take away this because see in silicon most of the time this gold is the dominant impurity there. So they can take down other impurity also, but it depends on the individual reaction kinetics.
Okay, sir.
So as you recall, your recombination rate is Np minus Ni square divided by tau p times tau n times p plus p1 plus tau n times tau p times n plus n1. Right? This equation all of you should remember. Okay. Now, if you are injecting a carrier, right? So your n become n plus n naught plus delta n, and p become p naught plus delta p. Right? Now, low level injection condition is still same. Right? So for low level injection, your delta n or delta p should be less than the majority carrier concentration. So less than p naught for p type, less than n naught for n type. Now, if ET is close to mid gap, your N1, P1, they are equal to Ni. But you remember, regardless of the ET level, the product N1, P1 is always Ni square. Okay. Regardless of the energy level, N1, P1 is always Ni square. But if the trap is close to mid gap, then they are basically equal and both are equal to Ni. Right? So, and of course, if let's say tau p is much larger than tau n, right? Then you have to ignore this other part, provided the factor that we are multiplying n and p, they are of the same order, right? So, for example, you consider, let's say, p-type material. So, for p-type material, p naught will be much larger than n naught. So, you can substitute here. Now, n naught p naught is Ni square, so they will cancel Ni square. So, what you will have here? P naught times delta n plus n naught times delta p. Now delta and delta p will be small if you are assuming low level injection, right? So you can just have let me write here, R is equal to n naught delta p plus p naught delta n. Delta and delta p I'm ignoring, and n naught p naught will be cancelled by Ni square divided by now if you see p naught is much larger than n naught, right? So you can write here tau n times p naught plus delta p plus p1. Now p naught is much larger than n naught, then p naught will be much larger than ni also, right? Which is p1. So you can just write here tau and p naught. So here is p naught times delta n, right? So p naught will cancel. You will have delta n by tau n. So for p type, your recombination rate will be delta n by tau n. Similarly, for n type, recombination rate will be delta p by tau p. In high level injection, you cannot ignore the product delta and delta p, right? So your numerator will become delta and delta p, right? Divided by both the terms will have delta and delta p. So you will have tau n plus tau p times delta and delta p, right? So one delta p will cancel, assuming that delta and delta p are equal. Your recombination rate will be delta p or delta n. So this is basically same as delta n by tau n plus tau p. This is for high level injection, correct? Where delta and delta. So this basically you can obtain just by substituting this thing here and assuming that delta and delta p are much larger. So all this n naught p naught will go away, right? Right. So what do you have here? Delta n by delta and delta p by tau p delta n plus tau and delta p, right? So if you assume that delta and delta p are equal, then you get this expression. Correct? So this is basically low level injection, and we have just given the expression for high level injection also, right? But you should always remember this is the expression, right? Right? Then by putting the values, you can see, what approximation to make and what approximation not to make. Now, when we will discuss about PN junction, right? You might have seen in your introduction to electronics also. When you connect the PN junction, right, you have a depletion region here, right? Now, what is depletion region? Can somebody define?
A region devoid of free charges.
So you mean there are no carriers? How is it possible? Like we have defined low level injection, right? How did you define low level injection? Delta n or delta p is much less than the majority carrier concentration, right? Similarly, we define the depletion region where electron and hole concentration is much less than the doping. You understand? See, if you have doping, let's say n doping or p doping, right? Or you can write effective doping here, right? So your electron or hole concentration will be equal to the respective doping, right? So if the concentration is less than that, we call it's depleted of carriers. So if you actually see the plot of hole concentration, it goes like this, right? So in this region there are holes, right, which is larger than n type, right, and smaller than the holes in p type region. But if you consider up to your metallurgical junction, this is p type and the hole concentration is less than the doping. In n type, electron concentration is less than the doping, right? So we call it depletion region. Now there are two things here. When you don't apply any bias, even in the depletion region, your NP product is Ni square. Your NP product is Ni square. And this depletion is called electrostatic depletion region, right? So your NP is less than the doping and NP is Ni square. That implies no carrier deficit. That means your R will be, what does it mean? What if NP is Ni square, R will be 0. So net recombination rate is 0. So that means if you are recombining 10 carriers, you are also generating 10 carriers. So net recombination is 0. Correct? Now, if you apply a reverse bias, then the carrier concentration really goes low here. If you apply a reverse bias, then in the depletion region, carrier concentration really goes low. And now NP is less than Ni square. Right? So in this case, there is a deficit of carriers because NP is less than Ni square. So in this case, there will be net generation, and net generation will be given by R, negative of R. Because this is not minus sign, this is basically just dash. So R is minus Ni square because NP is much less than Ni square. So you can ignore tau p times N1 plus tau n times P1. And if N1, P1 are Ni, you have basically minus Ni by tau naught. Tau naught is tau n plus tau p. So there's a net generation of carriers. So you have seen this thing in the PN junction diode, that there is generation current. Correct? There is generation current. Okay, just a minute, you can leave. I will just finish it. Only one more slide to go. Now this is just to differentiate bulk
Sir,
from
I have a
surface.
class. Can I leave?
Just 1 minute. This is just to differentiate bulk from surface. Now in bulk you have band gap, right? In surface, because there are dangling bonds here, so what will happen? You will have energy states even in the middle of the band gap, right? So if this is your band gap, in bulk you don't have any energy state here, but in surface you will have some energy state here. So there will be density of state which will be non-zero in the band gap region for surface, right? So this is the basically a message of this slide. Now you can see some measurement done here. This is for this blue line is for the bulk density of state measurement, and this is for surface, right? So you see this is a band gap here, but in the surface you see the density of state here. Similarly, another experiment, right? This is a bulk, this is a surface, right? So you see the density of state. So in the surface, even without impurities, right, you have states in the band gap, right? That means this there will be trap-assisted recombination at the surface, right? And that is called surface recombination. Now it is just for the completeness I'm telling you. You don't have to remember it. So similar expression we can also write for surface recombination, right? So you have this like Cn, Ptn, all those things, right? So now you have N1s, P1s, and your R become Ns, Ps, Ni minus Ni squared divided by. Now instead of tau p and tau n, we have 1 by Sn or 1 by Sp, where Sn and Sp are surface recombination velocities, right? And these are surface concentrations, right? So instead of per volume, it is per unit area. That's the only difference, right? And this SPN also written as C times NT. Now NT is a trap density, right? Or trap state density. So sometimes you may encounter there is a surface recombination. So this is a mechanism, right? So it is very similar to the trap assisted recombination, but it occurs at the surface due to the dangling bonds, right? And how you are going to calculate the recombination rate? You have this expression for recombination R multiplied by the density of states, because in trap you had only one energy level ET, right? Here you have multiple energy levels, right? So you have DOS, right? So now you have to multiply by the DOS and integrate over energy, right? So that will give you the surface recombination. Okay, so that's it for today. And so we have discussed different recombination generation process. They drive the system towards equilibrium. For indirect material, SRS dominate, and their coefficient depends on magnetic carrier lifetime, and which again depends on the cross section, trap density, and the thermal velocity. Okay, thank you very much. Those who have class, they can leave, and those who don't have class, if they ask a question, they can ask me. I'm stopping the recording now. No question, then I will close it. Thank you very much.